right now, I mean, literally at this exact second, there is this spherical bubble of radio noise just expanding outward from Earth in every
It's
direction.
happening right at the speed of light.
Exactly, at the speed of
Oh,
light. And it's our technological footprint, basically. This bubble is roughly 200 light years across. So if you're out there sitting on the edge of that sphere and you point out, really sensitive antenna at our solar system,
you're picking up some pretty wild stuff.
yeah, you're getting the faint static-laced broadcasts of like the 1936 Berlin Olympics. You're getting early radar pings from World War II.
The first episodes of I Love Lucy, right?
Right, exactly. We have been practically screaming our presence into the galaxy for almost a century. But, and here's the crazy part, when we point our own massive radio dishes back at the stars and we filter through all that cosmic background radiation to listen for someone else's technology,
Nothing.
we hear absolutely nothing. It is just dead silent.
And that silence is, well, it's deafening. I mean,
Yeah.
we're dealing with a scientific landscape that is defined entirely by an absence.
Which is so rare in science.
Oh, absolutely. Think about it. Most disciplines build on foundational physical evidence. A geologist has, rock strata they can touch. An evolutionary biologist has the fossil record.
But astrobiology is different.
Totally different. Astrobiology and really the whole broader search for extraterrestrial intelligence, it relies heavily on data we haven't acquired yet.
Right. And that's exactly what our mission is for today's deep dive. We're looking for the actual rigorous methodology behind how we're hunting for those elusive proofs, the specific signs, the evidence of their existence, or as the phrase goes, the dalil wa shawahid ala wujudihim.
I love that. And we really need to be clear with everyone listening. We are leaving the sci-fi tropes completely at the door today.
Oh yeah, no little green men, no flying saucers from Hollywood.
Right, no cinematic aliens. We're focusing exclusively on the hard data and the actual search mechanics across, astronomy, planetary science, and even intelligence gathering.
Because the tension driving this entire field is just this massive, glaring contradiction. We live in a universe that seems mathematically engineered for life. I mean, you look at the numbers, there are hundreds of billions of galaxies in the observable universe.
Each one with hundreds of billions of stars.
Exactly. So the statistical probability just screams that biology can't possibly be just this localized anomaly here on Earth.
This just doesn't make mathematical sense for us to be alone.
Right. But then the scientific method steps in and demands observable, repeatable evidence. And right now we have a sample size of exactly 1. So to understand how we even try to bridge that massive gap, we're pulling from a really diverse stack of sources for this deep dive.
We've got NASA's current astrobiology mission data, right?
Yep. NASA data, the historical archives from the SETI Institute, the philosophical modeling behind the Fermi paradox.
Which is always a fun one.
Oh, it's terrifying, actually. We're also looking at the European Space Agency's exoplanet catalogs, and this is where it gets really interesting. The official, declassified, unidentified aerial phenomena reports from the U.S. Office of the Director of National Intelligence.
Which is quite a mix. I mean, to really grasp this, it requires integrating disciplines that, frankly, rarely overlap.
Like what?
Well, think about an astrophysicist. They usually study stars and galaxies. But to find life, they suddenly have to understand the biochemistry of, lipid membranes. They need to know exactly what a biological byproduct looks like in a planetary atmosphere.
Right, they have to become chemists.
Exactly. While at the same time, you've got philosophers and statisticians using computational models of evolutionary bottlenecks to try and explain why the sky is so silent.
It's all connected. To kind of frame the sheer scale of the data problem for you guys listening, I always think of it like standing on an endless beach. Just trillions of grains of sand stretching all the way to the horizon.
Okay, I like this.
Mathematically, based on just the sheer volume of material, there has to be, let's say, a perfectly cubic grain of sand out there somewhere.
Right.
It has to exist.
Statistically, sure.
But your hands are totally empty. You can't just pick up random handfuls of sand and hope for the best.
You'd be searching for millions of years.
Right. You need a highly specific filtering mechanism. And in the search for extraterrestrial life, that mechanism begins with the most fundamental chemistry. We have to start the search for that core evidence by looking for the microscopic chemical byproducts of biology. We are hunting for biosignatures.
And we're starting that hunt right in our own backyard, in our solar system.
Which makes sense because, to find evidence of life, we have to start with the building blocks we actually understand. Right?
Exactly. And the focus on microscopic life is entirely driven by our own planetary history. People forget this, but Earth has supported life for roughly 3.8 billion years.
Right.
But for the vast, vast majority of that timeline, life here was exclusively single-celled.
Like just microbes.
Just microbes. Complex, multicellular organisms, animals, plants, humans. That's all relatively recent evolutionary development.
So we shouldn't necessarily be looking for, cities.
Right. The statistical baseline for our search assumes that if life exists elsewhere, it is overwhelmingly most likely to be microbial. So NASA's strategy for decades has been characterized by this simple mantra: follow the water.
Because where there's water, there's a chance.
Exactly. Liquid water is the universal solvent required for all known biochemistry. It's what facilitates the complex chemical reactions that allow organic molecules to assemble, replicate, and basically metabolize.
And we see that exact methodology playing out literally right now on Mars, right, with the Perseverance
Oh,
rover.
Perseverance is incredible.
It's hanging out in the Jezero crater. And, the selection of Jezero wasn't just some random spot they thought looked cool. Orbital spectroscopy showed that the crater contains smectite clays.
Which is huge.
Yeah, because on Earth, smectite clays are incredibly efficient at trapping and preserving complex organic molecules over long periods of time.
Because billions of years ago, Jezero wasn't a dry crater. It was a massive lake fed by a river delta.
Right. And Perseverance isn't just driving around taking surface pictures. It's actually drilling core samples from these ancient sedimentary rocks.
And the mechanism of that caching system, it's an absolute engineering marvel. It's designed entirely around the preservation of evidence.
How so? Like, what makes it so special?
Well, the rover uses a rotary percussive drill to extract these rock cores, right?
Okay.
And then they are autonomously sealed inside these titanium tubes.
Why titanium, though? Just because it's strong?
No, actually, titanium is used specifically because it doesn't outgas complex organics that could contaminate the sample. Plus, the tubes are coated in titanium nitride to prevent any chemical interactions with the Martian rock itself.
Wow. So they're keeping it perfectly pristine.
Exactly. And the instrumentation on board, like the Sherlock spectrometer, it uses deep ultraviolet Raman scattering to actually map the spatial distribution of organic molecules on the rock surfaces before they even drill.
Okay, wait. Raman scattering? I was reading about this. Basically, Sherlock fires an ultraviolet laser at the rock, right?
Right.
And when those photons hit a molecule, most of them just bounce off at the exact same energy level, but a tiny, tiny fraction of the photons actually interact with the molecular bonds of the target.
And they lose a very specific amount of energy in that interaction.
Yeah. And by measuring that exact energy shift, which is the Raman scattering, the rover can identify the specific chemical bonds that are present. So it can tell us if we're looking at like basic carbon or complex aromatic rings.
It's essentially reading a chemical fingerprint. But here's the catch. Even with all that amazing technology, Perseverance cannot definitively prove the existence of a past biosignature on its own.
Really? Why not? I mean, it sounds so advanced.
It is advanced, but identifying a definitive biosignature requires instrumentation that simply cannot be miniaturized to fit on a rover.
Ah, I see.
You are looking for something called isotopic fractionation.
Okay, what is that?
Well, life is lazy. It prefers lighter isotopes because they require less energy to process. For example, biological processes on Earth preferentially utilize carbon-12 over the slightly heavier carbon-13.
Oh, that makes sense.
So if we find a rock on Mars with an unusually high ratio of carbon-12 compared to the surrounding dead abiotic environment, that is a massive chemical red flag.
That's the evidence. That's the doll ale.
Exactly. But measuring that ratio with absolute certainty, that requires massive room-sized mass spectrometers.
Which you can't exactly strap to a rocket and shoot to Mars.
Right. And that is exactly why the Mars Sample Return mission is the critical next step. The goal is to bring those pristine, hermetically sealed titanium tubes back here to Earth laboratories.
That is just wild to think about. But, while we're hunting for essentially fossilized ancient evidence on a planet that's currently bone dry, the astrobiological focus has also expanded a lot to the outer solar system. Because out there, liquid water exists today.
Oh yeah, the icy moons of Jupiter and Saturn.
Specifically Europa and Enceladus. They present environments where biological processes could theoretically be happening right now as we speak.
Europa is fascinating.
It is, because if you look at it, Europa just looks like a heavily scarred, frozen wasteland. It's got this crust of water ice that scientists estimate is, 10 to 15 miles thick?
At least. And the ambient surface temperature is hundreds of degrees below zero.
Right, so it seems totally dead. But the physics of its orbit creates this completely different environment underneath all that ice.
Yeah, Europa is locked in what is known as a Laplace resonance with two of Jupiter's other moons, Io and Ganymede.
Okay, break that down for us. What does that resonance actually do?
So basically, their orbits are mathematically synchronized. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes 4.
Okay.
Because of this constant gravitational tug-of-war between the moons and Jupiter's massive gravitational well, Europa is forced into a slightly elliptical orbit.
So it's getting pulled and stretched.
Exactly. As it moves closer to, and then further from, Jupiter, the entire moon is physically stretched and compressed. This is called tidal friction. And it generates immense internal heat within Europa's rocky mantle.
Oh, wow. So it's heating up from the inside out.
Yes, the heat radiates upward, melting the inner layers of that massive ice shell, which maintains a global subsurface ocean of liquid water that is tens of miles deep.
And the volume of that water is just staggering. I mean, the estimates suggest that Europa alone holds twice as much liquid water as all of Earth's oceans combined.
It's mind-boggling.
But, and this is a big but, water alone isn't life. You still need a chemical energy source, right? Because underneath 15 miles of ice, there is zero sunlight for photosynthesis.
Zero. It is pitch black.
So any potential biosphere at the bottom of Europa's ocean would have to rely on chemosynthesis rather than photosynthesis.
Which isn't as crazy as it sounds because we see this exact mechanism on Earth.
Right, down at the bottom of the Marianas Trench.
Exactly. Around alkaline hydrothermal vents.
How does that work down there?
So at the ocean floor, water seeps into the rocky mantle, right? It reacts with iron-rich minerals like olivine in this process called serpentinization.
Serpentinization, okay.
Yeah, and that chemical reaction releases molecular hydrogen and a ton of heat. So this highly alkaline fluid, which is now rich in minerals and hydrogen, vents back out into slightly acidic, much colder ocean water.
And that contrast is where the magic happens.
Precisely. That interface creates a natural proton gradient. It's an electrical and chemical disequilibrium. And scientists believe that early life on Earth may have harnessed that exact gradient to generate ATP, which is basically the energy currency of the cell.
Wow. So if Europa's rocky core is volcanically active and it's interacting with that massive ocean, the same serpentinization processes could be continuously churning out the chemical precursors for biology right now.
It's a very real possibility.
Yeah.
And the crazy thing is, we don't necessarily have to figure out how to drill through 15 miles of ice to find out.
Because of Saturn's moon, Enceladus?
Exactly. The Cassini spacecraft basically proved this concept at Enceladus.
The tidal forces on Enceladus are so extreme that they literally rip fissures in the ice at the moon's south pole. They call them tiger stripes, right?
Yeah, you're a tiger stripe.
And the ocean water down there is under so much pressure that it's violently ejected out into space in these massive plumes of vapor and ice grains. And Cassini literally just physically flew right through those plumes.
It was an incredible maneuver. And the ion and neutral mass spectrometer on Cassini provided some unbelievable data during those flybys.
What did it find?
Well, as the ice grain slammed into the instrument at like 6 kilometers per second, they vaporized instantly. The spectrometer ionized the resulting gas and measured the mass-to-charge ratio of the particles.
And obviously they found water.
Right, water was expected.
Yeah.
But Cassini also detected molecular hydrogen. It detected nanometer-sized silica grains.
Why are the silica grains important?
Because those specific grains only form in extremely hot alkaline water. It essentially proved the existence of active hydrothermal vents on Enceladus.
Wow.
And, critically, it also detected complex macromolecular organics containing hundreds of carbon atoms.
That is just, it's the ultimate evidence-gathering scenario.
Yeah.
I mean, the ocean is literally venting its contents out into space for us to just fly by and catch.
It's very convenient.
It is. But unfortunately, this level of direct physical sampling is pretty much confined to our own solar system.
Yeah.
When we want to expand our search radius to the wider galaxy, to look for exoplanets orbiting other stars, we hit a massive, hard technological wall.
We do. We can't send probes.
No, we can't catch physical material. So our entire search basically relies on capturing and decoding the really, really faint light from distant stars, which is exactly where the James Webb Space Telescope, the JWST, fundamentally shifts our capabilities.
It's a total game changer because the challenge of observing exoplanets directly is basically a massive problem of contrast.
Right.
The host star is often billions of times brighter than any planet that orbits it.
I think the analogy I saw was it's like trying to spot a firefly fluttering right next to a military searchlight. from hundreds of miles away.
That's exactly it. It's blinding. Now, while some direct imaging is possible using coronagraphs, which are internal mechanisms inside the telescope that physically block out the star's light, the primary method we use for gathering evidence of biological chemistry is called transit spectroscopy.
Okay, so this is where we basically just wait for the planetary orbit to align perfectly with our line of sight, right? So the exoplanet passes directly in front of its host star.
Exactly. When that transit occurs, a minuscule fraction of the star's light passes through the thin ring of the planet's atmosphere before it continues its journey across the galaxy to hit the mirrors of the JWST.
And that atmosphere acts as a sort of chemical filter.
Yes. And the physics behind this are rooted in quantum mechanics.
Which always gets complicated.
A little.
Mhm.
But, simply put, when the starlight passes through the exoplanet's atmosphere, it interacts with the gas molecules. The electrons within those molecules can only exist in very specific quantized energy states.
Okay.
If a photon of light hits a molecule with the exact amount of energy required to bump an electron up to the next energy level, the molecule absorbs that photon.
Oh, I see. And because different elements and different molecules all have unique atomic structures, they absorb different, highly specific wavelengths of light.
Exactly. So when the JWST's instruments, like the near-infrared spectrograph, capture that light, they disperse it into a spectrum. And when we look at that spectrum, we find missing pieces.
Like dark absorption lines.
Yes. Those dark lines are essentially the barcode of the planet's atmosphere.
Yeah.
If carbon dioxide is present, for example, it absorbs light at exactly 4.3 microns, so it leaves a black line at that exact wavelength on the spectrum.
But it's literally a barcode. But the search for the DeLeo, the specific biosignatures, it relies on finding multiple gases together, right? Specifically gases in a state of chemical disequilibrium.
Right. Finding one gas isn't enough. Methane and oxygen are the classic example of what we're looking for.
Because methane is highly reduced and oxygen is highly oxidized.
Exactly. If you put them together in an atmosphere, especially one that's constantly bombarded by ultraviolet light from a star, they react very rapidly to form carbon dioxide and water.
So they should basically destroy each other.
In a geological blink of an eye. So if we use transit spectroscopy and we read a barcode that shows massive amounts of both methane and oxygen existing simultaneously, it implies that something is actively and continuously replenishing those gases.
Because otherwise they wouldn't both be there. And on Earth, that something replenishing them is the global biosphere. It's life.
Precisely.
But, you know, the planets we are targeting with the JWST aren't necessarily carbon copies of Earth, right? I mean, we spend a lot of time focusing on M-dwarf stars or red dwarfs, mainly because they are by far the most common type of star in the galaxy.
They are everywhere.
But because M-dwarfs are much, much cooler than our sun, their habitable zone, the Goldilocks distance where liquid water can exist, is much closer to the star.
Yes. And that proximity creates a massive variable for us. When a planet orbits that close to its star, the gravitational tidal forces eventually synchronize the planet's rotation with its orbit.
Oh, meaning the planet becomes tidally locked.
Exactly. One hemisphere perpetually faces the star, just
Yeah.
baking in eternal daylight, while the other hemisphere faces the deep freeze of space in perpetual night.
Which sounds completely inhospitable to life. But I was reading that atmospheric modeling suggests that the terminator zone, that thin ring of permanent twilight separating the day and night sides, could actually maintain a stable, temperate climate where liquid water and life might exist.
It's very possible. High-altitude winds could distribute the heat from the day side just enough to prevent the entire atmosphere from freezing out on the dark side.
Okay, but this kind of brings up a question for me, a fundamental debate within astrobiology. We're looking for liquid water, we're looking for carbon-based atmospheric disequilibrium, and we're targeting environments that share chemical similarities with Earth. It kind of feels like. It feels like we are trying to open a file on a computer without knowing the file extension. Like, we only know how to read .doc or .pdf, so we build our entire search architecture around finding those specific formats.
That's a great analogy.
But what if the universe is running on a completely different biological operating system? I mean, look at Titan, Saturn's largest moon. It has lakes, it has rivers, it even has a rain cycle, but it's entirely based on liquid methane and ethane at hundreds of degrees below zero.
Right.
So why couldn't life evolve using methane as a solvent and, say, silicon instead of carbon as a backbone? Are we blinding ourselves to alternative biochemistries simply because of our own Earth-centric bias?
It's a completely valid epistemological critique. And theoretical biology does explore alternative solvents like formamide or liquid ammonia. But the issue with silicon specifically is chemical stability.
Okay, how so?
Well, while silicon sits directly below carbon on the periodic table, and it can form four bonds, just like carbon, the silicon bond is much, much weaker than the carbon-carbon bond.
Ah, so it breaks apart easily.
Yes. Furthermore, silicon's bonds with oxygen are so incredibly strong that they form solid silica, basically rocks,
Oh.
right?
Yeah.
Rather than forming the easily broken, flexible bonds that are required for respiration and dynamic metabolism. Carbon's ability to form long, stable, complex molecular chains in liquid water is just unmatched by any other element we've studied.
So it isn't just a lack of imagination on our part. It's a limitation of instrumentation and really fundamental chemistry.
Exactly. We build telescopes to detect the absorption spectra of gases we know correspond to life, because frankly, we wouldn't even know how to interpret the data of a truly alien biochemistry. If we detect an atmospheric anomaly, we need an Earth analog model to verify it. We have to start the search using the chemistry we actually understand.
That makes total sense. We have to look for what we can verify. But, I mean, biosignatures only provide evidence of simple biology. The atmospheric methane produced by a planet of simple microbes is completely indistinguishable from the methane produced by a planet of complex, non-technological animals.
Right.
So, to find evidence of intelligence, a civilization capable of abstract thought and engineering, we have to stop looking at the chemical byproducts of their biology and start listening for the electromagnetic noise of their technology. And this brings us to the domain of SETI, the search for extraterrestrial intelligence.
Yeah. And for over half a century, SETI has relied on this premise that a technological civilization will either intentionally or accidentally leak electromagnetic radiation into space.
Because radio waves are just the logical medium for interstellar communication, right?
Absolutely. They travel at the speed of light, they are incredibly cheap to produce energetically, and critically, they pass relatively unhindered through the massive clouds of interstellar dust and gas that obscure visible light.
Right, visible light gets blocked easily, but radio punches right through. But they don't just listen to everything all at once, do they? I know the search is historically focused on specific frequencies, most notably something called the water hole.
The water hole, yes. This is a very quiet band of the electromagnetic spectrum, sitting right between 1.42 and 1.66 gigahertz.
Why is it called the water hole, though?
Well, at the lower end of that band, you have the emission line of neutral hydrogen, known as the 21-centimeter line. And at the upper end, you have the emission line of the hydroxyl radical.
And hydrogen and hydroxyl combine to form water.
Exactly. Because water is the foundation of life, physicists back in the 1970s theorized that any advanced civilization trying to establish a universal communication standard would choose this specific, quiet frequency band as a logical, universally recognized meeting place.
Like meeting at the water cooler.
Exactly. But the methodology isn't just about pointing a dish at the sky and turning up the volume. Natural cosmic phenomena like pulsars, quasars, the cosmic microwave background, they produce immense amounts of radio noise.
But that natural noise is different from artificial signals, right? Natural emissions are generally wideband. They smear across a wide range of frequencies, much like static on a television screen.
Right. Technology, however, produces narrowband signals. When we encode data into a radio transmission, we compress the signal into a very tight frequency range. We do this to conserve power and increase clarity.
Okay, a laser pointer is actually a really good visual analogy for this. It concentrates light into a coherent, narrow beam, unlike a standard light bulb, which just scatters light broadly in all directions.
That's a perfect way to picture it. If a radio telescope detects a sharp, highly compressed, narrowband signal that is isolated to just a single hertz of bandwidth, there's no known natural astrophysical process that can create that.
It absolutely requires an artificial transmitter. It requires intent.
Exactly. But the computational power required to filter all the cosmic static for that one specific artificial spike is just staggering.
Yeah, take Project Phoenix, for example. It was one of SETI's most rigorous campaigns. And they didn't just sweep the sky randomly. They utilized the largest steerable radio telescopes on the planet. They used the Parkes Observatory in Australia and the Arecibo dish in Puerto Rico.
Before it collapsed, yeah.
Right. And they systematically targeted 800 individual sun-like stars within a 200 light-year radius. They listened to millions of channels simultaneously, applying these complex algorithms to account for the Doppler drift.
Which is crucial because the Doppler drift is the change in frequency caused by the rotation in orbit of both our planet and the target planet. It constantly shifts the frequency.
And the data processing required for all that was so immense that it actually helped pioneer the whole concept of distributed computing. They utilized the idle processing power of millions of personal computers worldwide through the SETI at Home program.
It was brilliant. We had the largest telescopes on Earth, backed by a global supercomputer, analyzing the absolute most promising stellar candidates in our galactic neighborhood.
And the result of that rigorous, decades-long search? Scanning billions of frequencies for the most basic evidence of an artificial transmitter.
Nothing.
Nothing at all. We have found absolutely zero confirmed repeatable signals.
Now, we have detected anomalies, the most famous one being the 1977 WOW signal, which was picked up by the Big Ear telescope at Ohio State University.
Yeah, the wow signal.
It was a powerful narrow-band signal at 1420 megahertz, sitting exactly on the hydrogen line. And it lasted exactly 72 seconds, which is precisely how long an interstellar signal would remain in the telescope's beam width as the Earth rotated.
So it looked real. The intensity profile matched a distant point source perfectly.
Perfectly.
But despite pointing our most advanced instruments back at that exact coordinate in the constellation Sagittarius for decades, the signal never repeated.
And in science, an unrepeatable event cannot be utilized as evidence. Without the ability to reobserve and verify, the WOW signal remains an unexplained transient anomaly. It's a ghost in the machine rather than proof of contact.
Which is frustrating. And this comprehensive lack of data brings us to probably the most profound and disturbing philosophical framework in all of astrobiology, the Fermi paradox.
Enrico Fermi.
Yep. The paradox is named after the physicist Enrico Fermi, and the fundamental contradiction it highlights is the timeline. The universe is roughly 13.8 billion years old. The Milky Way galaxy is roughly 100,000 light years across.
Right.
But our solar system only formed 4.5 billion years ago. We are extreme latecomers to the party.
Very late. If you apply even conservative parameters to the Drake equation, estimating the rate of star formation, the fraction of stars with planets, and the likelihood of life evolving into a communicative civilization, there should have been millions of civilizations emerging billions of years before Earth even solidified.
And when you have a billion-year head start, you don't even need sci-fi faster-than-light travel to colonize a galaxy. You just need self-replicating spacecraft, known as von Neumann probes.
The math on those is terrifying.
It really is. If a civilization launches a probe to a neighboring star system at just 10% the speed of light, and upon arrival the probe mines asteroids to build 2 copies of itself, which then launch new stars, that exponential replication would saturate the entire Milky Way in just a few million years.
Which is a cosmic blink of an eye.
Exactly. Which leads directly to Fermi's famous question, where is everybody? If the galaxy should be teeming with older, more advanced life, we should see the evidence, we should detect their radio traffic, we should see their probes, we should observe the thermal signatures of megastructures like Dyson spheres altering the infrared output of their host stars.
The total absence of this evidence, this eerie silence, requires an explanation.
I picture it like holding a ticket to the most hyped, universally attended event in history. You walk through the tunnel into this colossal stadium. The lights are on, the infrastructure is perfect, the conditions are ideal, and the seats are completely, utterly empty. Not a single sound. When you are faced with that level of silence, you stop asking if anyone got an invitation, and you start wondering what terrifying event prevented the crowd from arriving.
And that terrifying mechanism is what we call the Great Filter, a concept proposed by the economist Robin Hanson. The Great Filter hypothesis argues that in the evolutionary pathway from dead matter to a galaxy-colonizing civilization, there is at least one step, a barrier, that is so astronomically improbable to pass that almost no species survives it.
It's a bottleneck of probability.
Exactly. And the critical existential question for humanity is whether the Great Filter is behind us in our evolutionary past, or if it is waiting for us in our technological future.
So let's look at both. If the filter is behind us, it means that one of the early steps in biological evolution is the freak occurrence. Perhaps abiogenesis, the initial jump from complex chemistry to self-replicating RNA, is a 1 in a trillion lottery win.
Or perhaps it is eukaryogenesis. On Earth, complex life only became possible because of an incredibly rare endosymbiotic event where an archaeon basically engulfed a bacterium without destroying it.
And that eventually formed the mitochondria that power all complex cells today.
Right. That single event took 2 billion years to occur on Earth. If that is the filter, then the universe is mostly sterile, and humanity is an incredibly rare survivor.
We're the lucky ones. But If abiogenesis is common, and if the evolution of complex brains is relatively normal across the universe, then the silence of the SETI search implies something far darker. It implies the Great Filter is ahead of us.
The filter ahead scenario theorizes that while species routinely reach our current level of technological adolescence, they universally fail to advance further. They hit a wall, because the energy required to manipulate spaceflight and advanced engineering is indistinguishable from the energy required to destroy a planet.
Wow, think about that. A civilization that develops the capability to launch relativistic kinetic projectiles, objects moving at a fraction of the speed of light, has effectively built a planet-killing weapon.
It's unavoidable. The same applies to self-replicating nanotechnology or engineered synthetic bioweapons. The Great Filter suggests that the intersection of biological aggression, which is derived from natural selection, combined with godlike technological power, is just a terminal equation.
So civilizations light up the radio spectrum for a fleeting moment, discover the mechanics of their own destruction, and just wipe themselves out. The silence we hear isn't an empty stadium, it's a graveyard. Every failed SETI search is a data point suggesting our own survival is statistically unlikely.
It is a staggering epistemological weight to place on a lack of data. We are looking deep into the void, finding nothing, and projecting our own potential for self-annihilation onto the silence.
But this entire paradigm assumes that the search must be conducted by looking out into depth space.
Yeah.
We have to completely change the parameters of our analysis when anomalies appear within our own atmosphere, captured by our own sensor networks. We have to analyze the data provided by the U.S. Office of the Director of National Intelligence regarding unidentified aerial phenomena, or UAPs.
Okay, before we dissect this data, we absolutely must establish a rigid analytical boundary. For everyone listening, the scientific analysis of UAP data is completely divorced from the cultural baggage of ufology.
Absolutely. We are not evaluating claims of extraterrestrial visitation. We are not endorsing hypotheses involving classified foreign drone technology. Both the left-wing and right-wing political spheres have their own narratives, and we are not taking any sides. We are operating strictly within the parameters of the declassified intelligence reports and the confirmed sensor data generated by military platforms.
Our sole objective here is to understand how anomalous data challenges our standard models of physics.
And the real paradigm shift here is the acknowledgement by the defense establishment that the data itself is real. Because for decades, the subject was relegated to eyewitness testimony, which is notoriously unreliable due to the limitations of human perception.
Right, but the modern UAP reports rely on multi-sensor fusion. We are talking about events where human observation is corroborated simultaneously by highly advanced, distinct technological systems.
Let's talk about the 2004 Nimitz encounter, because that serves as the foundational case study for this type of data fusion. The incident involved the USS Princeton, which is a guided missile cruiser equipped with the SPY-1 radar system.
The SPY-1 is incredible. It is an active, electronically scanned array, a phased array radar that doesn't rely on a rotating physical dish. It steers its radar beams electronically by shifting the phase of the radio waves.
Meaning it can track hundreds of hypersonic targets simultaneously with extreme precision.
Exactly. And the Princeton's radar operators tracked anomalous objects, which they dubbed anomalous aerial vehicles, descending from 80,000 feet to sea level in a matter of seconds.
Just dropping out of the sky. And when FA-18 Super Hornets were vectored to intercept, the pilots visually acquired an object resembling a smooth white cylinder. The famous Tic Tac.
Right. With no visible flight control surfaces, no wings, and no exhaust plumes.
Crucially, while the pilots maintained visual contact, the aircraft's onboard sensors locked onto the object. The Advanced Targeting Forward-Looking Infrared, or ATFL-IR pod, actually recorded the encounter.
And remember, infrared cameras do not see light. They detect minute variations in thermal radiation. If an object is burning fuel to generate thrust, it creates a massive thermal bloom.
But the ATFL-IR footage showed the object maneuvering dynamically without a detectable thermal exhaust signature at all.
Which makes no sense under our current understanding of propulsion. The intelligence reports categorize the behavior of these objects into a framework of 5 observables, which basically represent flight characteristics that fundamentally defy current aerodynamic modeling and material science.
Let's go through those. The first observable is anti-gravity lift. These objects remain perfectly stationary in high-altitude winds, or they perform complex maneuvers without any aerodynamic surfaces. There are no wings to generate lift, no rotors, and no buoyant envelope like a balloon.
The second observable is sudden, instantaneous acceleration. The sensor data indicates objects moving from a stationary hover to hypersonic velocities instantly.
And the physics required for that are incomprehensible. A human pilot loses consciousness around 9 Gs of acceleration. The radar data tracks these objects pulling maneuvers that would subject them to hundreds of Gs. At that level of force, the structural integrity of any known metal, composite, or carbon fiber would violently shear apart.
It would just be destroyed.
Hmm.
The third observable is hypersonic velocity without signatures. Pushing an object through the Earth's atmosphere at Mach 5 or higher creates immense friction, turning the air around the craft into superheated plasma.
It also creates a massive acoustic shock wave, a sonic boom, but the data sets show these objects traveling at hypersonic speeds without generating a sonic boom and without the thermal signature that should accompany that atmospheric friction.
The fourth observable is low observability. This is the ability to actively jam or evade sophisticated military radar, not just through geometric stealth design, but seemingly at will.
And the fifth is transmedium travel. The objects are tracked dropping from the upper atmosphere, plunging directly into the ocean without decelerating, and continuing to travel underwater at speeds that defy fluid dynamics. Striking the ocean surface at supersonic speeds is physically indistinguishable from hitting solid concrete.
It should obliterate the craft. The analytical dilemma here is severe. We have physical sensor data confirming the existence of objects performing outside the bounds of classical physics. The evidence is solid.
The data is real.
Yes, but the epistemological framework we use to categorize that evidence is broken. Think about it. An astronomer requires repeatability. If the James Webb Telescope detects a chemical anomaly on an exoplanet, scientists can point the telescope back at the exact same coordinates months later to verify the data. The scientific method relies on controlled observation.
But a military intercept is not a laboratory experiment. It is a transient, chaotic event driven by threat assessment.
Exactly. The primary objective of the intelligence community is binary. Is this object a threat from a foreign adversary or not? If they conclude the object is not a Russian or Chinese technological breakthrough, their primary mandate is fulfilled, even if the object's origin remains unidentified.
The military is not tasked with solving the mysteries of physics. They are tasked with airspace security.
Right. Therefore, the data remains siloed, lacking the rigorous peer review and continuous observation required by the broader scientific community to integrate it into a cohesive understanding of the universe.
This creates a massive logical friction, though, when we try to connect the UAP data back to the astrobiological search and the Fermi paradox. I mean, if the Great Filter is a real existential barrier, and interstellar travel requires an incomprehensibly vast expenditure of energy and technological evolution, it seems deeply anthropocentric and honestly logically flawed to assume a civilization would conquer the cosmos just to execute maneuvers in restricted military airspace without attempting formal communication. Why master the physics of the universe only to behave like a fleeting radar glitch?
It's a fair question. But applying human behavioral logic to an entirely theoretical, non-human intelligence is a fundamental analytical trap. We assume communication is a universal imperative, but an intelligence millions of years more advanced might view our radar systems the way we view the sensory hairs on a fly. It's just background noise to them.
That's a humbling thought.
It is. The difficulty lies in the fact that we possess rigorous, scientifically sound methodology looking for basic microbes millions of light years away, yielding no definitive proof. We have massive radio arrays listening for logical communication, yielding silence. And we have undeniable localized sensor data of physics-defying anomalies that offer zero contextual or scientific repeatability.
We are navigating a diagnostic wilderness. I mean, we began this deep dive standing on an infinite beach, overwhelmed by the statistical certainty that we cannot be the only instance of biology in a universe containing trillions of stars.
We examine the meticulous microscopic search for the basic chemistry of life, from the laser spectrometry of Perseverance, analyzing the smectite clays of Mars, to the potential for serpentinization at the bottom of Europa's subsurface ocean.
We explored the quantum mechanics of transit spectroscopy, using the James Webb Space Telescope to hunt for the chemical disequilibrium of methane and oxygen in the terminator zones of distant exoplanets.
We confronted the terrifying implications of the Fermi paradox and the cosmic silence. The realization that decades of filtering the 21-centimeter hydrogen line for narrow-band technological signals has resulted in nothing. suggesting that the Great Filter might be an insurmountable evolutionary bottleneck.
And we evaluated the epistemological divide in our own atmosphere, analyzing the multi-sensor military data of unidentified aerial phenomena objects that physically exist and defy aerodynamics, yet provide no verifiable answers regarding their origin or intent due to the differing standards of proof between national security and the scientific method.
The entire field of astrobiology and the search for extraterrestrial intelligence is defined by the friction between mathematical probability and the agonizing lack of physical proof.
We are a species desperately utilizing every tool across the electromagnetic spectrum to find a reflection in the dark, but the mirror remains frustratingly empty. However, the methodology of the search forces us to confront the fragility of our own existence. So I want to leave you with this final thought experiment to mull over. We spend immense resources hunting for a drop of water and a single microscopic cell. We assume that discovering a basic, single-celled organism on a distant exoplanet would be the greatest triumph in scientific history.
Which it would be.
But if tomorrow the JWST detects an undeniable, biologically driven chemical signature on a world 40 light-years away, proving definitively that basic life is common and easily formed, does that discovery make the eerie silence of the radio spectrum more comforting? Or, by proving that the universe readily creates life but fails to produce civilizations capable of speaking to us, does it confirm that the Great Filter isn't in our evolutionary past? Does finding a microbe millions of miles away simply prove that the mechanism of our own destruction is patiently waiting for us in the future? Keep analyzing the data, keep questioning the parameters, and keep searching the silence.